right, hello and welcome to section 4.5 on finite state machines. This is a section from the book Real-Time Computing for Mechanical Engineers. I'm Dr. Rico Piccone. Drs. Garbini and Devine are my co-authors on the book. MIT Press published it. Check out the website there for more info about the book, and the companion website for the book is rtcbook.org. So check that out. Finite state machines is what we're talking about today. A program that sequences a series of actions or handles inputs differently depending on what mode it's in is often implemented as a finite state machine, or FSM. Here, a state is a condition of the system for which there is a prescribed relationship between inputs and outputs, and between inputs and subsequent states. An FSM is an algorithm that maps inputs and states to outputs and new states. The mapping of one state to another is called a state transition. A state machine for which the outputs are functions of both the current state and the inputs is called a Mealy machine. A state machine for which the outputs are functions of only the current state is called a Moore machine. We'll mostly be dealing with Mealy machines. Here is the paradigmatic example of an elevator in a two-floor building. Modeling the elevator as an FSM, identify its states, inputs, and outputs. Determine whether it is a Mealy or a Moore machine. The elevator has four possible states: stopped on floor 1, stopped on floor 2, moving up, or moving down. Inputs include the buttons that are pushed in the elevator car and on each floor, and limit switches indicating that the car has reached each floor. The outputs are the commands to the lift motor, to the elevator doors, and the commands to the indicator displays in the car and on the floors. The outputs and the transition from one state to another depend on the current state and inputs, like the buttons. Therefore, this is a Mealy machine. Okay, state transition diagrams. An advantage of using state machines is that the necessary logic can be represented graphically in a state transition diagram. A state transition diagram shows the input-output relationships and the conditions for transitions among the states. Let's examine the left figure, this one, the state transition diagram for a simple example, and see how it might be programmed. This system has three states, A, B, and C. It has two inputs, the sequential count of an integer-valued clock K and a reset button R that, when true or 1, resets the state to A if the current state is B. We see for the three states here that A can transition to B, B can transition to C, and C can transition to A, but also B can transition to A under certain conditions. The outputs of the state machine are the variable O and the clock K. State transition conditions are evaluated at each clock count. The arrows between states are labeled as, on the left of the slash, condition for the transition. Then we have a slash, and then we have the output changes. So we have state A, which can transition to state B, given the condition that the clock count K equals 2. And if that is the case, the output O is changed to 1, and the state is now B. So we've transitioned to state B. State B can transition to state C if the clock gets to 4. Before that point, if R equals 1, that is to say, the reset button triggers a transition back to state A, then we set the output to 0, and we set the clock count back to 0. If we make it to state C, then we wait until the clock count is 6, we output 0, and then we output a clock count of 0. So we zero out the clock count again and go back to state A. So that is our state transition diagram. Starting out in state A, we could go from A to B, and then from B to C, and then from C back to A, as we do in the diagram at right, where we go from A to B to C. Then this next time through, we reset to A. We have the reset button R pressed. So while we're in state B, we then transition back to state A. So we short circuit C and we go back to A, and then we go back to B again. So the reset button has shortened our loop so that we go from A to B and then from B to A instead of going from B to C as we would usually do. Okay, that's just an example. And it's contingent on what happens with the reset button. Another representation of the information in the state transition diagram is the state transition table, such as the one shown right here. The table lists all possible transitions between states, the conditions that cause the state transitions, and the corresponding outputs. This representation is less suggestive of the overall topology of the finite state machine, but it is particularly helpful as a guide for programming. So we have the same state transition diagram above that's repeated here, and we have also an alternative representation as a state transition table. So the leftmost column is when state is in one of these states, and the input is one of these inputs. Then make the output O, output K, this and that, and make the next state this or that. Now, we have X representing irrelevant input. So the input in that case would be irrelevant for making the decision to transition states. And the small circle is no change in the output. So when state is A and the input is 2, regardless of what is happening with the reset button, we're going to make the output 1. We're not going to do anything in particular to the clock, but we'll make the next state B. So this represents the A to B state transition. When we're in B, starting in B, we can go either to C or back to A. This first row represents what happens when the clock gets to 4 and we've not hit the reset button. We'll transition to state C. Then we'll make the output 2 at that point, and we'll not do anything in particular to the clock, but we will make the next state C. When the state is B and the reset button is hit, regardless of what the clock is, we will make the output 0 and we'll make the clock count 0. So we'll reset the clock and reset the state to A. Finally, when the state is C, when the clock reaches 6, regardless of what the button is doing, we will make the output 0 and the clock K reset to 0 and go back to state A. So this is just an alternative representation of the same finite state machine. Programming finite state machines. So here's an overall strategy, a function for each state. We will now consider a systematic strategy for programming an FSM. The strategy is valid for any programming language, but of course we will use C. The first rule of the strategy is to write a function for each state. This function will be called repeatedly until a state transition condition is satisfied, and the function will implement any output changes and set the next state. Continuing the previous example where we have the 3 states A, B, and C, here is a function for state A. So in state A, we're waiting for the condition to be met, which is that the clock will be equal to 2. In this case, we will set the current state to state B, which we have to define this constant state B, but we can do that. And that will define what the next state is. And our output, this is O equals 1. So output change, the output will be changed to 1. The state transition logic is a little more complicated for state B. So if we have the reset triggered transition case, so if the reset button is pressed, then we're going to reset the current state to A and the output and the clock to 0. Otherwise, if the reset button is not triggered, then we'll wait till the clock is equal to 4. We'll set the current state to C and the output to 2. Of course, a state C function will also be necessary here. So these are states A and B, the functions we could define for A and for B. Now, the main loop. We have used a few global variables that can be defined as follows. So the current state, so we're going to make a state type variable, current state, and we're going to have an integer k for the clock counter and an integer o for the output variable. The type that we've used here, state type, with its constants state A, B, and C, can be defined as an enumerated type as type def enum, open brace, state A is 0, then state B will be automatically 1, state C will automatically be 2, and state type is the type we're defining. We need a main loop that calls the state functions according to the current state. Cur state is what we've called it. For a small finite state machine, an if structure would suffice, but for more complex state machines, this is unwieldy. It is much cleaner to use an array of pointers to the state functions. For our example, we can make an array of pointers to the state functions, so state A, state B, and state C, in the following way. So an array of pointers to functions can be constructed in this way, in this syntax. The values in state table must be given in the same order as those in state type. So this order has to be the same as this order. So we can call the state function that corresponds to the current state in an infinite loop with the following while loop. While 1, so this is going to be an infinite loop, it's always going to be met. We will repeatedly call the current state function. So the state table, we will get the current state. Current state is an enumerated type variable, which is going to be 0, 1, or 2. So we're going to be either in state A, state B, or state C, and we'll call that function from this state table that we've declared above. So the state table is a table of the functions. So we'll call the state A function first, then we'll call the state B function, and the state C function. Then we're going to insert code to wait a fixed amount of time. So the timing is something that we'll come back to and discuss more in the next section. But essentially, we can make our clock work by waiting some amount of time and then incrementing the clock count and repeating this so that we call a new state function approximately every so often in a periodic way. Obviously, if the state functions take different amounts of time to call, then it won't be at a constant rate, but more or less at a constant rate depending on the relative amount of time that the wait will take. So we'll talk about the timing in the next section. But in any case, we'll call the state A function or the state B function or the state C function depending on which is the current state. Then we'll wait an amount of time, then we'll increment the clock, and we'll start over again here, and we'll call whatever the current state function is and proceed accordingly. The final piece is to set the initial condition of the state machine. A call to the following function would work for the example. So initialize SM, takes no arguments and returns nothing. This is the initial condition, setting of the state machine to an initial condition. So we set current state to state A to start. We set the output and the clock to 0, and this would be our initialization routine. in the book, listing 4.1 combines these ideas into a single C program. It's a little long to show on a slide, but it's listing 4.1 in the book. This programming strategy is quite general and can be applied to many forms of finite state machine. It will be applied in lab exercise 4 to implement a basic user interactive PWM motor driving technique. So we'll have a finite number of states we will be cycling through, and we'll write state functions for each state. Okay, so that is finite state machines. I'll see you next time.